So we will now be taking a special case and try to derive what the angular velocity of the frame M would be if E3 dot in the F frame is equal to 0. Okay, so this is somewhat of a simplification of the case which we have done in the previous section, and this is quite useful in practical problems. Okay, not all the three axes have this uh, uh, time derivative not equal to 0. Many a times one of them would be equal to 0, and in that situation how would the angular velocity of M look like is what we want to see over here. Okay, this is a case of plane motion, so let me just define that first. A rigid body M is said to have plane motion relative to F if all its material points, I hope you can still recall how we defined the material point. Okay, there was a continuum hypothesis. All its material points have plane trajectories in parallel planes. So how do we achieve this situation that E3 dot with respect to F is actually equal to 0? You can do it by some manipulation in terms of how you orient the coordinate systems. So when you choose E3 attached to M, remember E1, E2 and E3 were attached to M in a direction normal to the planes of trajectories then relative to the F frame E3 moves parallel to itself. This implies that E3 dot with respect to F will be equal to 0. So this is something which you should be able to visualize. Okay. Go on. Okay. You have to be sure that E3 dot is actually equal to 0 in this case. So this has application in many rigid in many real life situations. Okay, and when you look at them in the frame of M, there will be a plane motion because all the material points will be following a plane trajectory, and it is also clearly easier mathematically because the number of terms in the mathematics would be less, and hence it would be easier to treat. Okay, obviously you will be missing out on one of the coordinates which is, say, not in the motion of the plane, okay, not in the plane motion, say perhaps in the thickness direction for a solid. Okay, so we have the degree of freedoms of plane motion. This is equal to 3. It is 2 for translation, okay, in the xy or whatever direction you want, and 1 for rotation. So for a rigid body, okay, this is for a rigid body, not for a point particle, obviously, okay. We left that boat long back. We have been talking about rigid bodies. Okay. There is another important point to note over there, that for a plane motion, E3 dot is equal to 0, but the converse is not true. Meaning if E3 dot is 0, then it does not necessarily mean that you have a plane motion, okay. So the example of this is, we have seen this several times, the motion of a nut. It goes without saying that everything in our course is actually rigid, okay. So I am not writing a motion of a rigid nut, okay, on a fixed bolt is not plane, okay. We had seen that it was a general motion, but if you attach E3, okay, to the nut, let me try to draw that easily, okay. So if you have this as your nut, okay, and this is your E3, then as nut moves, E3 dot will be equal to 0, but it is not a plane motion, okay. So that's why we say that just by the fact that E3 dot is in frame F is equal to 0, it does not mean it's a plane motion, okay. So clearly you have your, I'm just showing the nut separately. So this is your, sorry, this is the bolt, okay. So the axis of this nut and the bolt are the same. So let's see how we write this. Let's draw a frame F like always. We will, let me draw that here. Okay, so I have a E1, I have a E2, and I have a E3. This is F, okay. Now you have this frame M, okay. I keep on saying frame M and frame F, but they can be two separate rigid bodies in a mechanism, okay. In a machine, for example, there may be two separate parts of a machine with one moving relative to each the other, okay. Now let me draw the other coordinate system over here, okay. Let me use this ink. Let me say that this is the point, okay, and this is E1 hat, this is E2 hat, and this is E3 hat, okay. This is point A. Okay, let me just show that. This is point O. Okay, so just okay, so for case like this, okay, this you can show for the, not exactly like this, let's not call it a nut, but let's see the motion of a screw. How does the screw look like? Okay, and then say this is the head, and there are these threads, and using your screwdriver you apply, so it's like a wrench, okay, that you have already seen. Now this keeps on moving inside. Okay, this is how the screw works. So for the motion of a screw and plane motion, we have E3 dot with respect to F is equal to 0. We can choose E3 equal to E3. See, if this is the axis along which this is moving, okay, this will always be equal to 0, okay, and hence if this uh, sorry, E3, yes, if this particular thing is always 0, we can choose it in such a way that it coincides with the E3 of the F frame. This is clearly the M frame, okay, since we are discussing the angular velocity of M, that's why this is the M frame, and we can choose it in a way just because it's not changing with time anyways, okay, and that we have shown in this diagram. Now once E3 is chosen along the big E3, okay, the small E3 is chosen along the big 3, there are some conclusions which you can make, okay. One of them is that E1 and E2 have no component along E3. Why is this true? Because E1 and E2 will have no component along E3, okay. This is because even E2 and E3 are parallel, orthogonal, and since E3 is equal to big E3, hence we are saying that even E2 will not have any component along E3. Now let theta of t be the angle between E1 hat and E1 at time t. Okay, so let me try to show you that over here. It's the angle between E1 and E1, small e1 and big E1. So if this is the line along small e1, this is the line along big E1, okay, so clearly this angle is theta at a given time t. Okay, so it might get slightly messy, that's why I'm not writing, and I'm writing this as E3 because we have chosen it in this form. Reason we could do it because E3 dot with respect to F was 0. Okay, so let theta be the angle between E1 and E1 at time t. Now when that is the case, we can write E1 of t is equal to cos theta of t E1 hat plus sine theta of t E2 hat, and it's needless to say that ER for all times will be equal to E3. Sorry. Okay. Now this particular thing, writing what we have just done is we have written this vector E1 in terms of the basis vectors capital E1, capital E2. Clearly there will be no third component of capital E3. Okay, and the way we could have written it is using this cos theta and sin theta. Okay, if you are not sure how this is written, you can always see something like this: E1 dot E1, okay, should give you a cos theta, just because you have defined the angle in that particular way. So that will help you. Using direction cosines is another way you can go about it, but I think both of them should be okay. Now similarly you can write the vector E2 in terms of E1, capital E1 and capital E2. That would just be sine theta of t E1 hat plus cos theta of t E2 hat. Okay, and E3 dot with respect to f is equal to 0. Okay, that's anyways where we started off. We just wanted to write both of them, and since E1 dot has to be now found and E2 dot has to be now found, since E3 dot is already found out, so E1 dot with respect to f is equal to minus sine theta E1 plus cos theta E2 theta dot. Okay, then you have theta dot as E2 hat. How do we know this? Well, this particular thing is equal to E2. Okay, that's why we have written it like this. So I'll just rub it out, and similarly I will be now writing E2 dot with respect to the frame F. So E2 dot with respect to frame F will be just differentiating now this one with respect to time. Okay, so let's see, that would be minus of cos theta E1 minus of sine theta E2 theta dot and theta dot E1. Okay, so that's why you have this E1 dot, E2 dot and E3 dot. Now we want to write equation 1.47. So please turn back and check what it was. Okay, this was omega of t is equal to half of ei of t multiplied by ei dot of f at time t. This was equation 1.47, and we want to do that over here. Write equation 1.47. Please check the derivation of equation 1.47. Okay, what it was. Okay, now clearly there is an index notation and I is the repeated index, so you would have I equal to 1, 2 and 3 over here. So this would imply that omega of time t is equal to half into E1 cross E1 hat dot with respect to f plus E2 cross E2 dot with respect to f plus E3 cross E3 dot with respect to F. Half so E1 you want to write, so let me just looks it needs to be better written. Okay, so now you have E1 cross E1 dot, you have E2 cross E2 dot, and you have E3 cross E3 dot. Okay, so let me first write it like this: E1 hat cross E1 dot, if you see, is actually equal to theta dot E2. Similarly, E2 dot is minus of theta dot E1 hat plus E3 hat cross 0. Okay, because E3 dot is equal to 0. Now you can use the cross product rule, and you will find out that this quantity is equal to theta dot E3 hat. This quantity is also this one. Okay, this quantity is equal to this quantity is also equal to theta dot E3 hat. So this will overall become theta dot E3 hat. And theta dot is what we write as omega. This implies that omega of t is equal to theta dot E3 hat. Omega is equal to omega E3 hat with omega is equal to theta dot. Okay, this is 1.52. Okay, so you want to physically write what omega is, and we have had some discussions about it before. So omega is definitely the rate. Omega is the rate of rotation of E1 relative to E1. Okay, how do we know? Well, please see this. Sorry. Please see this figure. Okay, theta is the angle between small e1 and big e1, and hence when we say that omega is the rate of rotation, that means it's the rate change of this angle theta. Okay, it's the relate of e1 relative to big e1. Okay, that's the first thing, there was no doubt about that. Now it is also the rate of rotation of any line LM perpendicular to E3 hat fixed in M. Relative to any line LF perpendicular to E3 hat fixed in F. since phi dot is equal to theta dot plus beta dot, let me just show you these symbols, is equal to theta dot. Let me now show that. So let me choose a nice color. Red is a good color to go. Okay, so let me draw that any line LM. Okay, so this is that any line LM. Okay, PQ. Okay, and this angle is beta between PQ and E1. Okay, so this is LM, and this is clearly perpendicular to E3. Okay, small e3, because it is lying in E1 E2 plane. Now the other line is LF, that's over here, for example. ST. Okay, between points S and T, and this is called LF. Okay, so this angle is, say, this angle first will be theta, and clearly an incremental angle beta. Okay, so this will be theta plus beta, and if, sorry, this is not correct. We must draw the angle from O. Okay, so the angle gamma is drawn. And how is this gamma drawn? Well, it is just like PQ is not actually originating from A. Similarly, ST is not originating from O, but it is still perpendicular to big E3. So ST is perpendicular to big E3, and PQ is perpendicular to small e3. Okay, this is LM, this is LF. So this solid line which you see is actually in the direction of LF only. Okay, it's a unit vector in this direction, and hence this meets at this point R, and this angle is theta plus beta plus gamma. Okay, so you should be able to check why this particular angle for this geometry should be theta plus beta plus gamma. Okay, so again, theta dot is definitely the rate of rotation of E1 with respect to E1. It is also the rate of rotation of line LM with respect to E3. LM perpendicular to small e3 fixed in M, and then relative to any line LF perpendicular to E3, big E3 in fixed in F. So because this particular angle phi is the change of LM with respect to LF, and if you look at this particular figure, phi dot will be equal to theta dot plus beta dot plus gamma dot. Now unfortunately beta is fixed on M, so beta dot, which is beta is over here, this angle cannot change with respect to E1. small e1, since e1 is also fixed in frame f. So this will be equal to 0, and by the same logic gamma dot will also be equal to 0. So that's why you have that theta dot will also represent the change of sorry, okay, we are here. Okay, it is also the rotation of a line LM relative to line LF, since phi dot is equal to beta dot is equal to gamma dot. Okay, and that is equal to theta dot clearly, because beta dot and gamma dot is 0. So in this special case, what's the special case which we have just discussed? Omega is the rate of change of a finite angle theta. Now if you have a general spatial motion, meaning not a planar motion like what we have been discussing, this infinitesimal rotation is not the small change in a finite angular measure. So this not true for spatial motion. Spatial motion means if the rigid body is moving in 3D, then omega is not the rate of change of the finite angle. Okay, and omega is also not equal to the rate of change of a finite angle. So omega is not equal to theta dot in that case. So this is something which you should be remembering, that all this is only true for a planar motion. Okay, the rest of the part is quite straightforward over here. So if you have, say, omega is equal to omega E3 hat is equal to theta dot E3 hat, this implies that omega dot is equal to omega, sorry, okay, you can just differentiate with respect to time, you will get E, okay, because E3 dot will be equal to 0, and this is clearly double theta E3 hat, and this can be written as alpha E3 hat. Okay, this implies that alpha is equal to theta double dot is equal to omega dot, it is equal to d omega by d theta by dt. Okay, we have been doing this many times in this course, and this is equal to omega into d omega by d theta. This is equation 1.53, because d theta by dt is actually omega. Okay, this particular term is actually omega. So if you are ever given this situation that theta double dot is equal to alpha, and alpha is a function of omega theta t. Remember, we have done this for the acceleration, where acceleration was a function of position, velocity in time. Okay, so similarly is the case for this alpha as well. Then you can do these integrations. You will require two initial conditions, just like last time, or one at the beginning, one at the end, whatever works. Okay, so two initial conditions at t equal to 0 and theta equal to 0 is equal to theta naught, and theta dot is equal to 0 is equal to omega naught. Okay, And again, if omega is a known function of only one variable, like theta, omega or t, okay, then this 1.54 can be integrated by separation of variables. So they will be very similar to 1.32 to 1.35. Please see these equations. Okay, so theta, omega, alpha will replace s, vt and alpha t. So for uniform acceleration, for uniform rotation, so these are very similar expressions to 1.32 to 1.35. So please derive them, and actually most of them are already derived while I was writing this. Okay. So one can one 1.55 to 1.58. Okay, straightforward, but don't skip it. So in this section we want to find the relationship of the velocity and acceleration of a material point between the F frame and the M frame. Okay, so we want to see if the velocity and acceleration of a material point is defined in M frame, what would its velocity and acceleration be in the F frame. Okay, so that's something which is relevant, because you may have one body moving with respect to the other and the velocity is defined with respect to one of them. What would be the velocity of the same point or a point on this with respect to the other part? Okay, so that can happen, and it can keep on adding itself, I mean, to as many parts as there may be in a machine or a system. Okay, so consider a reason why we would want to do this. Let me just give you one example, which at this point should be easy for all of us to understand. A simple visualization of motion relative to a frame M moving relative to the ground frame. The ground frame. Okay. So consider this case. The flow of gases. You must have seen videos of rockets taking off, okay, from the earth. So a flow of gases through the nozzle of a rocket engine has a simpler description relative to the frame M attached to the rocket than the ground. Okay, because I mean the rocket will move in slightly complicated trajectories. I mean, definitely not linear, but with respect to the frame of reference M attached to the rocket, it will always be moving away from the rocket. Okay, so that makes it quite simple. And there are many other examples or motivations you will see during the course when you start attempting certain examples and problems. Okay, So let's have a physical picture first, okay, like a diagram. So let's call this as frame F. Let's call this as frame M. This point is O, okay, A, P, and then RPA, RP of T. Okay, so the point P in motion, okay, material point P on a rigid body is in motion, then VP, F and AP with respect to F are its velocity, velocity and acceleration with respect to the F frame, and then you have V, P and with respect to M, and acceleration of P with respect to M with respect to the M frame, and they are somewhat related by omega of F and omega dot M of F. Okay. So that's what we want to find eventually, and how is these two things playing a role in the relation between the velocity and acceleration in terms of frame F and frame M. Okay, so we have shown in this figure the position vector of point P as RP T, and then we have shown the O is definitely fixed on this F, A is fixed on M, okay, and clearly the point P is also being observed from M, and that position vector is being shown by RPA, okay, let me RPA at any given time. Okay, so that should give us RP of T is equal to RA of T plus RPA of T. Okay, this can be called as equation A. Now we take a time derivative with respect to the F frame, so that way we will write R of P with respect to F is equal to R dot A with respect to F plus R PA dot with respect to F. Okay, now the second term, which is this term, can be written in terms of R dot PA. Remember, there was a relationship, a constant vector in M can be written how? It can be written as R dot PA by M plus omega cross RPA. Okay. So this is something which you should revise. Just see that derivation again. Okay, it was a constant vector in the frame M, and RPA is constant in M. Okay, because it is with respect to that frame. So please see that once. Okay. Now this automatically means that the velocity, I mean this RPF, R dot PF can be written as the velocity of P with respect to F, can be written as the velocity of A with respect to F is equal to omega cross RPA plus Vp with respect to m, because r dot pa in frame m is actually the velocity of this particle with respect to m. So this is the term. Okay, this equation is called 1.59. Okay, now we want to again take a time derivative of this equation, because we want to, so here what we have done, we have found the velocity of this material point P in frame F and the material point P in frame M. Okay, so we have found that relationship over here. So we want to do the same for acceleration. So to do that, we just differentiate this equation with terms of time. Okay, that would give us acceleration of p with respect to f. Okay, and sorry, let me just write it completely. So acceleration of p with respect to f, well, taking a time that would be v dot p, then we would have acceleration of a with respect to f plus omega dot omega, sorry, every time we take a time, so then the next step is to take a time derivative of this term. Okay, and clearly there will be a chain rule applied. So first would be omega dot with frame f cross r pa, then the next would be r dot pa. Okay, sorry, omega cross r dot pa with respect to f plus, and then you have a d by dt of this term, so d by dt of velocity of p with respect to m in the frame f. Okay, now this term is can be written as plus that same terms omega dot with respect to f plus, sorry, cross rpa, then omega dot. Okay, this one will be done, this is a r dot pa is a constant vector, so that can be written in f, this can be written as rpa of m dot, okay, rpa is a constant vector in m plus omega cross rpa. Okay, and this next term which you see over here, this can be done using equation 1.50. Okay, what does 1.50 state? Let me just write that. Okay, okay, actually we have just used 1.50 over here also, sorry for this particular term. Okay, this entire thing is coming up from that, this entire square bracket which you have. So d by dt of fm will be equal to, now d by dt of vp of m with respect to m plus omega cross v of p with respect to m. Okay, so this is coming up from, let's see what it was. I think I should write it for the sake of completion. maybe it's just better, right? But you should go back and check the derivation of 1.50. So this was 1.50. Any vector derivative, time derivative in the f frame is equal to the same vector's derivative in the m frame plus omega of m with respect to f cross. Okay, so we wanted to write the time derivative of Vp of velocity of p with respect to m frame in the ground frame, and that is equal to the same in terms of m plus omega across RPA. So this is what equation 1.5 is, and we have just used that. Please go back, pause the video, go back and check that derivation, and then come back over here. This means we can write the acceleration of p with respect to f as the acceleration of a with respect to f plus omega cross RPA plus omega cross RPA plus 2 omega into Vp of m plus acceleration of p. Okay, this is 1.60. So let's see this term as it is, this term as it is. Okay, this term is basically this and this one. Okay, and this cross this is actually contained over here, and this 2 time is coming because once this omega into Vpm is coming from over here, and then the second is coming from over here. Okay, so until there that is clear. Let me just remove all this. Okay, and the very last term, acceleration of p with respect to m, is essentially this particular term. Okay, so this is the acceleration of point p in terms of m. So this is the relation which we have. 1.59 is the relation between Vpf and Vpm, and relation 1.60 is the relation between the acceleration APF and APM. Obviously what you would require is omega vector and RPA and omega vector and omega dot vector, okay, and RPA. Okay, so that is what we have over here. So we now want to focus on this term omega cross RPA, okay, this particular term, and see how this can be understood more, because it's slightly complicated. Okay, let me first draw it. Okay, so if this is the frame M, this is the point A fixed over here, and this is the point P. So this vector is PA or this vector is AP. Okay, so this is vector AP, and you have this written over here. Let's say that omega is in this direction and this direction is E hat. Okay, omega of this frame M. Let's now write this term omega cross RPA, or we can just write it as omega cross AP. So this is a vector triple product, formula of which we have already seen several times. This would be omega dot AP into omega minus omega dot omega is written as omega square AP. Okay, and then you take a minus sign, we can write it as AP minus AP without the vector sign, okay, because omega dot AP is omega AP and cos theta, where theta is the angle between AP and omega, this one, okay. So this is AP cos theta in the direction of E hat, okay. So that's what we can write over here. And if we now draw this as a perpendicular, let's say uh, D over here, okay. Let's draw this D over here, point D, okay, and clearly this would become a vector AD in that situation. So this would be vector AD. This is over here, okay, and this will clearly be vector DP. Now if I want to write this as minus omega square, sorry, it should just be omega square without the vector sign, okay. Omega square AP minus, now AP cos theta is actually the vector AD, okay. AP cos theta in the direction E, okay, this is the direction E, is actually vector AD. You can take the projection AP and see how it falls over this particular line which you have drawn, and this can be written as minus omega square into dP, okay. So this particular term omega cross AP is actually the product of the square of angular speed of a rigid body M and the perpendicular distance of point P from angular velocity vector omega of M drawn through A. And is always directed radially in towards this vector, okay. So this vector dP which you have is actually omega cross AP, and you can see its direction. Okay, so this is important actually. What I write over here, you can visually understand what this is, but you should also at this stage of your life have the ability to write these things in words, okay. This is important, and if you find doing this hard, please practice doing this more to be able to write mathematics in terms of words and then to be able to write words in terms of mathematics. Both of them are very important, and that interchangeability makes a lot of difference, because when you are trying to understand yourself and once you have understood, you are trying to explain it to someone else, you need to be able to convert from maths to words and words to maths. Okay, so please don't ignore sentences like this. I write this for you to stop, pause the video, think about it, convince yourself, and then move ahead. Okay, so this term omega cross AP has a name which you are all familiar with. Okay, so omega cross AP is called the centripetal acceleration. Okay, so centripetal means center seeking. And the term 2 omega cross VPFM, okay, where did it go? This term, okay, this is called the Coriolis acceleration. This is named after G. Coriolis. Okay. Now, using this particular figure, if you can take the case of a special motion of a frame M, what is the speciality about it? Well, one is that E3 hat is equal to E3, then it would mean that omega is equal to omega E3. Okay, and so for points A and P in same plane normal to E3, omega dot AP would actually be equal to 0. Okay, and omega cross AP would actually be equal to minus omega square AP. Okay, so this is a special case where omega is the vector omega is equal to omega E3. Okay, and if A and P are in the same plane normal to E3, that omega dot AP will be equal to 0, just because the angle between them would be 90 degree. Okay, so this is something which you can note. Okay, so we'll continue later with the kinematics related to translation frame T. Okay, we can move ahead and discuss the kinematics relative to a translating frame T. Okay, so if you have a frame T, okay, which translates with respect to F, the frame F. So that is what we want to consider over here. The earlier case, the frame M was rotating with respect to F. Okay, right now it is translating with respect to F. Okay, so let's see how this goes. So first off, you have to define. So you have a frame T. Okay, sorry. A frame T is set to translate with respect to frame F if displacements of all its points ABC are same in F. Okay, so let me show that with a diagram over here. You have a frame F, okay, and then so I'll draw the frame like this. It has a point A, it has a point B, it has a point C, okay, and E1, E2, E3 are the coordinate axis. So this is a T frame. So now we have B1, we have A1, A1, and we have C1. Okay, so the displacements of all its points A, B, C and as many other points that you take are same in F. So the displacement of B going to B1 and A going to A1 and C going to C1 is exactly the same. This is delta RB, this is delta RA, this is delta RC. This would imply that the velocity and acceleration of all points in T with respect to F are same, because since delta RB is the same as delta RA is the same as delta RC, so velocity is just the time derivative of this with respect to frame F. They will also be the same. And if we want to write that mathematically, velocity of BA with respect to F is equal to R dot BA with respect to F, and it is equal to VB with respect to F minus VA with respect to F is equal to 0. Okay, the relative velocity of B with respect to A is 0. This means that delta RBA is a constant vector in F. Okay, so delta RBA is a constant vector. This is a conclusion based on the fact that delta RB, delta RA and delta RC are all the same. What about the acceleration? This will be equal to 0 just because the velocity of BA in the F frame is 0. Okay, since the velocity is 0 of BA, the time derivative of this, which is the acceleration, will also be 0. So let's say it in words. The relative displacement velocity and acceleration between any two points of t with respect to frame F are 0. Okay, so we have shown all that. Okay, the displacement, the relative displacement, velocity and acceleration between any two points. So B and A were the points which we had over here, but the same would hold true for any point in a translating frame. Clearly, T is a translating frame, so that's why I don't have to separately say that anymore. Okay. Another important point is that the motion of just one point of t is necessary and sufficient to describe the motion of t. Now if you look at this figure, suppose you had the motion of point B given to you. Okay, you have the displacement of it between any two time intervals. The same exact displacement would be there for A, would be there for C, and for any other point on this frame T. Okay, so that is why we are saying that if you know the motion of just one point of this frame, then that is necessary and sufficient to describe the motion of the entire frame. Okay, because the entire frame will be translating according to the same descriptions of that one point. Okay, this also means that all the directed line elements of T are constant in F. Okay, we have clearly seen that in the figure. Okay, this means that EI of F dot is equal to 0. Actually, when I am writing, I should write it as a 0 vector, because this is not just in magnitude, it's also in direction. So all the directed line elements of T are constant in F. Well, see this, take this directed vector E1. Let's say it's between this and this point initially. Okay, this is E1. Now since this will translate to the same description, this will also have the same displacement. So E1 will always remain like this. Okay, in this translation, and that is why they are saying that E1 dot with respect to the F frame will always be equal to 0. Okay, so E1, E2, E3, all of them will be equal to 0. And once that is there, then equations 1.47 and 1.50 will give. Okay, we had done the most general case earlier on. So let's see. So we had 1.47 as omega of t is equal to half into ei cross ei dot with respect to f. So you can see that translation is being made as a special case of a rotation. Okay, and 1.50 over here is what, any vector in the f frame is equal to any vector in the m frame plus omega m by f into, so 1.50 is this. Let's see now what we get out of it. The only thing is we'll replace this m over here with t, okay, because we are referring to a translating frame. So let's see what these two equations become. 1.47 over here will become omega of t is equal to half into ei cross ei dot with respect to f t. This will become 0, okay, just because this particular quantity is 0, and this implies that omega dot will also be 0. Omega dot will also be 0. Also, it would mean that any vector in the f frame, the time derivative of any vector in the f frame will be the same as time derivative of the vector in the t frame, just because this omega is constant. Okay, so this is called equation 1.63, and it is much more simpler as you can compare with the previous descriptions of m. Okay, so that makes a lot of difference in the mathematical treatment of translating frames. Okay, we can also say, we were trying to see this conclusion from the other side. If omega of t is equal to 0, then for any length, any two locations a comma b of t, RBA is equal to omega cross RBA is equal to 0. Okay, this would imply that RBA at time t will be the same as RBA at time 0. Okay, and this would mean that RB at time t minus RA at time t is equal to RB A. Okay, this implies that displacements of all locations of t are same. This implies that t is in translation with respect to f. Okay, so what we have done from over here to over here is go back from this, okay, to where we started with the definition of translation. So if omega is equal to 0, okay, for any frame, then that would mean any vector RBA would have a time derivative which will be equal to 0 according to this particular relationship. Okay, you should recall from which equation has this come from. Okay, I mean the answer is already over here. And then okay, and then you will say that RBA at time t will be equal to RBA at 0. After that you can just break down these two terms, okay, into the respective position vectors at given time t and initial time 0, and this would mean that the displacements of all locations of t are the same. Okay, how would that mean? Well, RB of t minus RB of 0 is the same as RA of t minus RA of 0. Okay, so with this you can say that the displacements of all locations of t are the same and that t is a translating frame. So that's what we have done over here. Now let's try to use equation 1.63, 1.59 and 1.60. okay, what all will they give? We want to uh, use them to find the velocities and accelerations of point A with respect to t. Okay, so 1.63 is there, 1.59 and 1.60, you should go back and check what it is. The reason I tell you to go back and check is that you can see also the derivation of that. So you should pause the video and go and check the derivations of 1.59 and 1.60. Okay, so let me write 1.59 for you. That is V of P by F is equal to V of A with respect to F plus with respect to F plus omega dot AP. Okay, we had derived this, remember? So there should be no confusion about how each of the terms had come up and what each of these terms physically mean. Okay, since we have done it in so much of detail, you shouldn't have that doubt. Okay, so 1.63, 1.59 and 1.60, all of these three things we want to combine now. I should also put 1.63. okay, that just means that in the translating frame this is the same as that in the t frame, the time derivative of any vector. Okay, so velocity of p with respect to f is equal to velocity of A with respect to F plus omega is clearly 0, so we can't write that, and T, as I've said, is to be written over here. Okay. Similarly, E A of P with respect to F is equal to acceleration of A with respect to F plus omega is 0, omega dot is 0, so you are just left out with this one. Okay, so this is equation 1.64, and this is the relationship between Vp and of a point P with respect to a point A on the translating frame. So just to recap what we have, this is the frame F, this is the frame T, okay, and you have a point A on this frame and the point P is somewhere over here. So what is the velocity of P in terms of velocity of A? Similarly, what is the acceleration of this point P with respect to the acceleration of point A? So that is what we are doing. Okay, it's a simplified case of what we have dealt with before. So VA of F, AA of F being the same for all points, right? Because the displacements of all points of t are the same, hence the velocity and acceleration of all points will also be the same. Okay. Now you have to use 1.63. What was 1.63? Since it has gone from the screen now, I'll write it as over here. Okay, this is 1.63. So you can write velocity of P with respect to F is equal to velocity of P with respect to T. Okay, I'm writing the first term, and then the second term, velocity of A with respect to F, can be written as velocity of T with respect to F. Since the velocity of point A will be the same as the velocity of the whole frame or the rigid body, okay, that's why this can be done. Similarly, we can write the acceleration of P is equal with respect to F is equal to acceleration P with respect to T plus acceleration of T with respect to okay. So these velocities and accelerations which you see in equation 1.65, I mean velocity of P in the F frame or velocity of P in the T frame or acceleration of P in the F frame or acceleration of T in the F frame, they can all be expressed either in Cartesian, cylindrical or path coordinate. These are the three coordinates which we have taken, okay, we didn't take the spherical one, and you can just add them up according to any basis vector you want, okay. Now let me just come back to this figure. So E1, E2, E3 will also remain the same, okay. We have already discussed why when we said about the directed, okay, all the directed line elements of T, that's where we meant this. And then let's go to another translation, okay, it's the same frame but I'm not able to draw it as well, but again E1, E2 and E3 will be here, and then you will again have a A2, C2, B2, okay. So if you see the path of A, okay, I can draw it something like this. So this is path of A. So path coordinates can also be used for all this, okay. velocity of A with respect to F, velocity of acceleration of A with respect to F, and so on. That can be used over here. Okay. Let me now come back. Let me draw this another figure over here. Frame F, P, and this is the T frame, this is the F frame. Okay, not correct. Okay, so this is say R PA at time t, E1 hat, E2 hat, E3 hat. And this particular vector, this is O clearly, so this is RA of t. Okay, and this is RP of t. Okay. Now you can use this equation 1.65 and let's take a point Q. This is just to show that you can keep on adding them, the relative velocities and accelerations. So the relative velocity of PQ with respect to F is equal to clearly the velocity of P with respect to F minus velocity of Q with respect to F. Velocity of P with respect to T plus velocity of T with respect to F. Okay, that's coming from over here, this equation, minus, you can write the same for Q, so this will be velocity of Q with respect to T minus velocity of T with respect to F. So this term and this term will get cancelled. I should not show this. Okay, this term and this term will get cancelled and you will get velocity of P in the T frame minus velocity of Q with respect to the T frame, or this is equal to the velocity of PQ in the T frame. Okay, so this tells you that the velocity of vector PQ in the F frame will be the same as the velocity of the vector PQ in the T frame. Similarly, you can use this equation, acceleration ones, to prove that the velocity of PQ in the F frame is, the acceleration of PQ is equal to acceleration of PQ in the T frame. So, saying that in words, the relative velocity and relative acceleration of point P relative to Q in all reference frames in mutual translation are same. So this translation word is important. Okay, all these things are getting 0. The basic point was omega getting 0. Omega and omega dot being 0, all these expressions of relative velocity and acceleration, or the velocity of point P with respect to point A on the M frame, and so all became very easy. So that's what it looks like in words. Okay, now if you have this equation 1.65, okay, you can still see that 1.65 over here. You can keep on breaking them down into as many reference frames as you want. Okay, so let me show that to you, and that will be quite important when you solve very complicated mechanisms, okay, systems in which one part is moving with respect to the other, which itself is moving with respect to the other, which itself may be translating with respect to the other, and so on. Okay, so let's see. So the 1.65, it should be here. Okay, 1.65 may be compounded for several translating frames. So if T1 translates relative to T2, sorry, T1, if T2 translates relative to T1 and T1 translates relative to F, then we can write that the velocity of P with respect to F is equal to velocity of P with respect to T2 plus velocity of T2 with respect to T1 plus velocity of T1 with respect to F. Similarly, the acceleration of P with respect to F, acceleration of P with respect to T2 plus acceleration of T2 with respect to T1 plus acceleration of T1 with respect to F. Okay, so if one wants to visualize this, this is say the frame F, and then you have this, I'll just show the frames like this. This is the T1 frame, and then this is the T2 frame. Okay, so it will have its own coordinate system, it will have its own coordinate system. Let's call it A, let's call it B, and if you have a point P, okay, somewhere over here, so this is the, okay, all translating frames. These lines show the path of A and B. So any point P which is over here like this, it can be written, the velocity of it can be written in the F frame, and acceleration can be written as in terms of the F frame using these expression. Okay, so let's take up a real life example for this. Sorry, okay. Let's take it over here. And then one can have something like this. So these are all links. Okay, so think of it like a uh, engine which is trying to move a vehicle or a locomotive, train, something like that. Okay, let me show you all that frame. So let's call this the 1, 2, 3, 4, and then we have 5 and 6. Okay, so let's see how we can describe this. So the degrees of freedom of a translating system are 3. Okay, clearly x, y, z in the Cartesian system. Okay, or any other system which you would want to describe. So if t is constrained to move on a given surface or a curve, then degrees of freedom will be 2 or 1, okay, respectively. Now we can see that if it's along a curve, it will just be a path coordinate, so you would require only one independent coordinate. Okay, and it will be called a plane translation. So what would be the degree of freedom will be equal to 2, or a rectilinear translation. So one frame which you have over here in this diagram is of the main body, 2 is of the piston of the engine. This is a time to actually stop and see how a IC engine works, an internal combustion engine. Okay, you should pause the video, go look up some sort of a animation which shows you how the piston assembly makes cars and bikes and trains around us move. Okay, so please do that. 3 is the piston rod, 4 is the crosshead, so all of these in the motion, and you will have to understand this motion. Okay, that's your sort of homework. This will be a plane translation, and the coupler rods 5 and 6 will have a rectilinear translation. So you should see and learn about the working of IC engine. IC is internal combustion. How cars move. Okay, this is something I think you will do, and then you should be able to identify that the frames 1, 2, 3, 4 in this diagram actually represent a plane translation, and the coupler rods 5, 6 have a rectilinear transformation. Okay, a rectilinear translation. Sorry. Okay. So that's where we finish this particular topic. The next topic which we would want to learn is the rigid body kinematics. Okay, so if let's have a figure over here. Again, it's this frame F, then you have this rigid body M, this is O, this is the point P in this is the point A in this, this vector is RPA, also as AP. Okay, this is O, this is RP, this is RA. Okay, for material points P and A of a rigid body M, okay, the velocity of P with respect to M is equal to 0. Acceleration of P with respect to M is equal to 0. Okay, if ever I forget writing a vector sign over 0, please do it yourself. Okay, but you should understand that when I say 0, it's both, it's a vector and hence its magnitude is 0. Okay, and then you want to write equations 1.59 and 1.62. So I do not want to write 1.59 again, but you should check that over here. Okay, 1.59, 1.60, then 1.61 and 1.62. All of them have to be written. Okay, so equations 1.59 and 1.56. So I will do is I will write it in red so that you know how to derive this. Okay, you should be able to derive all this. So velocity of P with respect to F will be equal to velocity of A with respect to F plus omega cross RPA. Acceleration of P with respect to F is equal to acceleration of A with respect to F plus omega dot cross RPA plus omega cross RPA or AP, whatever you want to write. Okay, velocity of P with respect to F can be written as velocity of A with respect to F plus omega cross AP, and then the acceleration of P with respect to F is the acceleration of A with respect to F plus omega dot cross AP plus omega cross So it is 1.66, 1.67, 1.68 and 1.69. The velocity of PA is equal to omega cross RPA using this expression, okay, velocity of P minus velocity of A. Similarly, the acceleration of PA in the F frame is equal to omega dot AP plus omega cross AP. Okay, or RPA. That's 1.70. Okay, so RPA is this vector over here. Okay, so we are able to write the relative velocity of P with respect to A. So, I mean, one of the points to note is that RPA is a constant vector in M. Okay, so similarly, the time derivative, you remember there was, this is with F, for any vector F, for any vector M, okay, plus you had an omega and the vector in M. So here you put that constant vector and RPA dot will be equal to 0 in M, so this becomes 0 and hence this becomes velocity of PA. So that's how you can also get this one. Okay. So let's now take a plane motion, okay, for rigid body. For a plane motion of a rigid body with Ez equal to E3 equal to E3. So I hope you know that the small E3 is attached to the M frame and the big E3 is attached to the F frame. So omega will be equal to omega Ez. Now for its material points A and P, in the same plane normal to Ez with AB is equal to RER. Let me show that over here. Let me draw this M over here. This is clearly having omega, So the point A is over here. So it's this point, okay? This point A. What I'm doing in that figure over there is this point A is now my base, and then I draw the X and Y axis. Why? Because it's a plane motion. Point located at this R, okay, it will have a ER hat, it will have a E5 hat, and you have this angle phi. So this point can be called, this point B can be called as sitting at a coordinate r comma phi. Okay, so AB will be equal to RER. Now you can see that, okay, you have seen how ER and E5 are also defined over here. So okay, let me show this with a different color, this coordinate system. Okay, okay, now one can say that the velocity of BA is equal to omega cross AB is equal to omega into EZ. Okay, that's what we had as our omega. Cross AB can be written as RER. Okay, this would make it omega R E5. Similarly, so this is all coming from equation 1.68. Okay, 1.68. Sorry, not 1.68, this 1.70 actually. So from 1.70 you can write this, and 1.70, and similarly the acceleration also is over here. This will be equal to omega dot cross AB plus omega cross AB cross RER hat minus omega square RER hat. So this can be written as minus omega square RER hat plus omega dot R E5 hat 1.71. Now if you want to show that, okay, the acceleration of BA would have two components, one along ER, that is omega square R. Since it's a minus sign, so I have taken it away from ER, and then the other component is along E5, that is omega dot R. So that will be, so this is a, that come out, oh, okay, so you have this as omega dot R, okay, and acceleration will be a resultant acceleration of BA will be this summation of this and this vector summation. Now let me reinstate this M. Okay. Okay. Relative values correspond to a circular motion of B relative to A, with AB rotating at the rate omega. Okay, fine. So you can physically now interpret how ABA looks like. Okay. So we want to now move to the so-called instantaneous axis of rotation. Let's see how it goes. A rigid body is said to have an instantaneous axis of rotation at time t if all its points, okay, now when we say point, it can mean either material point or points on rigid extension. Okay, see, we had used this definition of points in the above derivation just now. Okay, so you should be able to clearly identify in a given situation what was actually a material point and what was the point on its rigid extension. Okay, on such an axis have zero velocity at that instant. A rigid body is said to have an instantaneous axis of rotation at time t if all its points on such an axis have zero velocity at that given instant. Okay, one of the most important point is that it does not always exist. Okay, let's see. For a given angular velocity omega of the body and the velocity va of its point A, so A is this again the same point in on this body, or you look at this particular diagram. Okay, the instantaneous axis of rotation exists if I find a point B such that, let's see, for a given angular omega of and velocity VA of its point A instantaneous axis of rotation exists if we can find point B such that the velocity of B must be 0. So the velocity of P is equal to velocity of A plus omega cross R BA. Okay, this is coming from equation 1.70. Please go back and see this. Okay, and this must be equal to 0. That is, the velocity of A must be equal to minus of omega cross R BA. So there are many possibilities, okay, where the instantaneous axis of rotation will exist, okay, and for that obviously this E has to be satisfied. Now so there are a few ways in this can be satisfied. One is that if you have VA dot omega is equal to minus of omega cross RBA dot omega, okay, and this is equal to 0. Solution exists. Okay, so we can say that the instantaneous axis of rotation. Any reasons why this value should be equal to 0? I think it's a good puzzle to leave you with. Okay, I put a question mark in red. You have to tell why that is equal to 0. Okay, so the instantaneous axis of rotation exists only if dot omega is equal to 0. That is, if either the velocity is equal to 0 or velocity of A is perpendicular to omega. Clearly omega cannot be 0, okay, and this is not the case which we are referring to right now. So yes, so this particular thing is what we have taken, okay, and that gives us that this must be equal to 0, and the ways this can be equal to 0 is either if the velocity of A is equal to 0 or that the velocity of A is perpendicular to omega. Now here is an important part about this, that the instantaneous axis of rotation will always exist for a plane motion, since the velocity of A will always be perpendicular to omega. Let me put that in words. Rotation always exists for plane motion of uh, rigid body, since velocity of A is perpendicular to omega. The point I at which this axis exists or intersects the plane of motion of A is called the instantaneous center. So obtained using Vi is equal to Va plus omega cross Ria. Okay, so this is again coming from 1.70. This implies that omega cross Va is equal to minus omega cross omega cross Va by omega square. Okay, so this exactly tells us the position vector of this I, the instantaneous center, with respect to point A. Okay, so you can easily locate that. For instantaneous center I, clearly the velocity of is equal to 0, but generally the acceleration is not equal to 0. This is because this position Ri keeps on changing, so there are different points of body are instantaneous centers at different instants. Okay. Okay. Now what I'll do is I'll draw this diagram of A, okay, from coming from over here, and I want to basically break this again into this radial and angular components, and let me just show that again. Okay, we want to now see all this in terms of the instantaneous center and the instantaneous axis. So let me draw this over here. Okay, you have the point A, you have ER hat, you have E5 hat. Okay, now the velocity of A, which you see, is actually equal to omega into IA. Okay, let me write all that separately first. I should just draw the coordinate system over here. Okay, let's see the velocity of points A, B, C, whose plane of motion is through I, can be expressed as, so this is the plane of motion is through I. Okay, that's the important part. And the IA, IB and IC can be written as, let's call this over here, this is point C, this is point B, this is point A, ER hat, E5, this is B, VB, VC, okay. So velocity of A with respect to the velocity of I plus omega cross IA is equal to, again, omega Ez, sorry, I'll write it separately. So Vi will clearly be 0, okay, so that will leave us with omega Ez hat cross Ia is the Ia distance with the ER, okay, because Ia is along ER. This would mean that this is equal to omega Ia into E5 hat. Okay, so that's why we can write the velocity of A is equal to omega Ia. I am not showing the direction. Okay, I am showing the direction. It is along E5, but the magnitude is I omega Ia. Okay. This would imply that you can write VA by IA is equal to VB for any other point, right? IB for any other point C will be equal to just the magnitude of omega. Okay, from this expression we can write that. So that has been shown, all that over here. So the velocity of C, velocity of A and velocity of B are all in this direction. Their magnitudes are what? Omega I b. This magnitude is I will not show the vector sign because the direction is clear. This will be omega I c. This will be omega I a. Okay, and this is again omega. So this is equation 1.72. So the magnitude of the vector VA of a point A equals the product of its radial distance IA from I and omega. That's something which is seeable from this equation, okay, which has come up from this one. And the direction of VA, as you see, is along the direction of E5. Okay, and how you can achieve this is by a suitable rotation. So let me write that in words. Focus on this diagram when I write this. VA is directed along normal E5 to IA obtained by rotating IA about A. Okay, rotate IA about I, sorry, about I in sense of omega. Okay, so if you rotate IA about A in sense of omega, you get this E5 direction. Okay, so please you use your right hand thumb rule and see whether all this is making sense. Right hand thumb, okay, all of them. So equation 1.72 implies that if this omega is equal to 0, then IA would be tending to infinity. Okay, this means the instantaneous center will be at infinity, and this happens in plane translation. Okay, I remains at infinity since so consider this situation. Okay, if you have the velocity of B and A are known, okay, and they have the same plane of motion that we are already showing by this omega, so it's the same plane of motion and they are known at a given instance, then the instantaneous center can be located in several ways, okay, by just using this expression. So for example, if VA is not perpendicular to VB, then I will lie at the intersection of normals to VA and VB, and if they are parallel to each other, so let me show that in slight detail. So for a rigid body, in plane motion, if the directions of VA and VB having same plane, of motion are known, the velocities are known, at a given instant, then center I can be located let's say case 1, if VA is not parallel to VB, and this is the best way to show, okay, then let me show that. If you have this, if this is a point B, okay, this is a point A, and this is a point A. If this is the direction of VA and this is the direction of VB, now it does not mean that it has to be a plane motion, okay, it can be like something like this, so that at this instant the velocity of B is in this particular direction, okay. So if this is the case, if VA is not parallel to VB, then I is at intersection of normal to VA, VB at A comma B. This is I, okay, normal to VA and VB, this is the point of intersection, and this is I, okay. If let's say if VA is parallel to VB, say you have a situation which looks like this, you have the point A, then say you have the point B, both of them are parallel to each other, okay, then I is at infinity, and this would mean that VA is equal to VB. Then you take the case 3, let me just draw it once more, okay, you have velocity of A, velocity of B, this is point A, this is point, sorry, this is point A, this is point B. So if VA is parallel to VB and AB is perpendicular to VA, so AB is perpendicular to VA, it will clearly also be perpendicular to VB. Okay, then I can be found out something like this. And you can use the similarity of triangles to say that IA by IB is equal to VA by VB. Okay, that's easily coming in from over here. Where did it go? Over here. Okay, IA by IB is equal to VA by VB. So then I will be on the intersection of this particular line. Okay, this is not the only case where this can happen. You can have a situation like this, where for example VA is like this, VB is like this. Okay, this is B, this is A, this is AB, and VA is perpendicular to AB. Okay, and then you can have your instantaneous center somewhere like this. So you can again use, this angles will be like this. Okay, if this is a special case of this, if VA is the same as VB, so VA is the same as VB, AP VA VB, okay, then I is at infinity again. So this is a special case of case 3. So there are several such situations. If you have if you have a body which is say a cylinder like this rolling without slipping, okay, then the instantaneous center is over here, okay, because at this given time it will feel as if this is rotating about this point I. Okay, so there are many situations in which you can find out the instantaneous center of instantaneous center of rotation. Okay, and it will only be useful for finding velocities. Okay, remember at this point the velocity is 0, not the acceleration. Okay, and you can choose this as your origin or your starting point, so that because this particular term will always contribute a 0 velocity. So you can write the velocity, say, of this point C, transfer it from I to C, okay, and then that would be just a omega term will be there. Okay, so that would be R omega, velocity of C, center of this. Okay, and if it was not in terms of this I, then you would have to know that velocity. Say if you were trying to write the velocity of C with respect to this point, then you would have to know this velocity to be able to write that. Here that's easy. So that makes it's quite useful, and you will perhaps be learning more about it in examples and problems which you yourself do.